Hi everyone. Today I'll talk about my research project in the bank group, which is about hot carrier cooling in quantum dots. Nowadays, both climate change and depletion of natural resources are a major concern worldwide. It's therefore important that we all know that fossil fuels won't last forever. So it's therefore important that we come up with alternatives. And quantum dot solar cells are seen as promising devices that can use solar energy to generate electricity with potentially very high efficiencies. So quantum dots are materials with a few nanometers in length that can transport electrons. And they are interesting because their properties depend on their size and shape. For example, you can see here that each dot emits a different color depending on its size. We can therefore make different types, and they can be used in many different applications. And this is also the character that makes them very appealing for use in solar cells. However, their performance in solar cells is often limited by a process whereby the energy captured by the sun is lost instead of being converted into electricity. And this is known as hot carrier cooling. So here I'm modeling the quantum dot in terms of energy levels, and each electron in the quantum dot can occupy these levels. And if the electrons are in these lower levels, then they have less energy than if they're in the higher levels. And you can see that these levels are all close together and they form the valence band. And similarly, these higher levels are close together and they form the conduction band. So when we shine a light on a quantum dot solar cell, high energy electrons are formed in this conduction band. And ideally, all of these would be converted into electricity. However, they tend to relax very rapidly to the edge of the band gap. So this is something we want to avoid to get high efficiencies. So our first question is, how does this process actually happen? Because there are many suggestions, but there is not an exact explanation. So my main work is to apply GPU accelerated electronic structure calculations to model nanomaterials in order to investigate this process. And here I'm showing a model cadmium selenide quantum dot that we designed. And our calculation shows with this model that this process actually occurs via conical intersections. And to understand what these are, imagine you're on a path, and then another path that leads downhill intersects your path. And since taking this downhill path would be easier than continuing along your main path, then there's a very good chance that you're going to change your path to take the one that leads downhill. And this is how you can think of the quantum dot during the hot carrier cooling process. So by analyzing this process, with this new method, using different quantum dots, we can determine how this process and its rate can be controlled by changing the structure of the quantum dot. Thank you.
The application of these, is the idea that these would be painted on in a thin film, or how would they actually be, become part of a solar panel? You know what I mean? Yeah, how does one quantum dot become a solar panel?
So what happens is it's, inside like the solar cell, you have the quantum dot and you attach it to like a larger, like a semiconductor that has like a large band gap. And then, so what happens is when you shine light on it, you get your high energy electrons, and then the electrons, you're going to want them to be injected into the semiconductor. And then from there it goes like to the internal circuit, and then that's how they generate the electricity. So
yeah, I was just curious. So the quantum dots, they become a thin film on top of that semiconductor, or are they actually individual little structures that get laid down?
Yeah, I mean, I'm not sure about that one. Sorry, I'm not sure about that.
Do you have an estimate of how much energy is lost during the process?
Yeah, so like on a long time scale, pretty much all of the energy is lost. So there's so what we want is obviously potentially, if we can capture these electrons before they're lost, we can therefore put them back in to the system, and then we can have that higher efficiency that we want.
How do you go about fixing the conical intersection you find one? How do you then change the structure?
So like we just model different you know, quantum dots. And then the idea is, you know, this one has your like ammonia ligands, but the idea would be to like add, you know, different ligands like, I don't know, carboxylic acids or something like this. And we can also, you know, this has 26 cadmiums, but we can also go a lot higher and, you know, change the size and, you know, maybe do 33 or maybe 100 cadmiums. And then we can see like how the process is gonna change depending on the structure.
Okay. So you're basically in the process of figuring out what knobs there are, and then you figure out.
Yeah, exactly.
Okay, cool. Thank you.